Hello, everyone. I'm Yupeng Zhang from the University of Maryland. Today, I'm going to present our paper, vRAM, Faster Verifiable RAM with Program-Independent Preprocessing. This is a joint work with Daniel, Jonathan, Dimitris, and Babis. So in this paper, we are considering the following scenario where there is a computationally weak user who wants to delegate the computation of a program P on a particular data X to a powerful server and receives the result P of X. And this scenario has a lot of applications in practice, especially with the fast growth of cloud computing. So right now, there are many cloud service providers like Google, Amazon, and Microsoft, and all of us are using their services, delegating our data and computations to the cloud. Cloud computing provides a lot of benefits, such as reducing the local computational resources and also the effort to maintain the local servers. But in this scenario, it also raises some security concerns. And one of these concerns is called integrity. Namely, how can you guarantee that the result returned by this server is correctly computed by this program on the data? So a cryptographic solution to this integrity problem is called verifiable computation. So in verifiable computation, we call this user as the verifier and call the server as the prover. And verifiable computation asks the prover to further attach a proof to this result and allows the verifier to validate the correctness of the result using this proof. And the security guarantee is that even if this prover is malicious, which means he can do whatever he wants, it is infeasible for the prover to return a wrong result and still pass the verification. So this is the security model of verifiable computation. However, this is actually the best model we hope to achieve, but in most existing solutions, because of the efficiency reasons, we also require the existence of this preprocessor who is responsible to do a setup phase and send some public parameters to the verifier and the prover before the whole execution of the verifiable computation. In verifiable computation, we are interested in the following efficiency measures. First, we have setup time, which is the time for the preprocessing phase. And then we have prover time and prover memory, which is the overhead we introduce on the prover side to generate this proof. And then we have proof size and verification time. For your information, using existing techniques, we can already achieve very good verification time and the proof size. But usually the bottleneck is on this prover time and memory usage. Namely, in order for the prover to generate this proof, we need to introduce an overhead of 6 to 8 orders of magnitude on this prover side compared to merely running the computation. And this is the major part we are trying to improve in our work. And in addition, the scope of our paper is, as the name indicates, we are trying to support validating arbitrary programs the verifier wants to check in the random access memory machine model. And this is called generic verifiable computation on RAM programs. So the prior work in the literature of verifiable RAM can be roughly classified into 2 categories. And the first category is called program-dependent preprocessing. It requires the program to be known ahead of time by the preprocessor to generate the public parameters. And the public parameters depends on this particular program, and the verifier can only use it to validate the same program, but potentially running on different data. And because of the program is known ahead of time, usually the program-dependent preprocessing systems can achieve a relatively better prover efficiency. But if the verifier wants to validate another program, she needs to run the preprocessing again, which is very expensive and must be trusted. The second category is called program-independent preprocessing, meaning that the processor only needs to do one-time setup, and later the verifier can use it to validate arbitrary programs on any data. But because of this generality, the prover efficiency is much worse compared to those systems with program-dependent setup. So the major in our paper, we are trying to propose a new construction called vRAM that achieves the best of both. So our solution is in this category of program-independent preprocessing, meaning that we only need one-time setup and later can be used to validate arbitrary programs. But in the meantime, we improve the prover time by around 1 order of magnitude compared to existing systems with program-independent setup. And this is actually comparable to, and sometimes even faster than, those systems with program-dependent setup. In addition, we also improved the memory usage on the prover side by around 2 orders of magnitude. So next, I want to show you a little bit more details about the verifiable RAM constructions. So for all the existing solutions on verifiable RAM, including ours, we are all following this two-step paradigm. In the first step, we are going to construct a circuit that checks the correct execution of a particular RAM program. More formally speaking, the circuit takes the program as the input together with the data X and a claimed result Y, and outputs 1 if and only if Y is the correct result of executing the program P on the input X. Okay? And we call this part the front end. And the reason why we're building this front end is because we have many great prior work in the literature of verifiable computation that builds very efficient systems for validating the outputs of a circuit. And we can actually use one of these schemes to build a backend on this particular circuit. And in this way, we can construct a verifiable RAM construction, because the result the verifier received from the prover must be correct if this circuit outputs 1. So this is the two-step paradigm we have in the verifiable RAM constructions. So in this talk, I'm going to focus more on explaining the front end. So now let's think, how can we build a front end, how to build a circuit to validate the execution of a RAM program. Then we need to think about how the RAM program actually works, right? So basically, we have a CPU which contains a state of several registers, a program counter, a bunch of flags, and so on and so forth. And for a particular RAM program, think about like assembly code with a bunch of instructions. The CPU is going to read the first instruction, do the addition in this case, adding the values in 2 registers, put the result in the first register, and moves to the next state. Okay? And similarly, the CPU is going to read the next instruction, do the multiplication, and moves to the next state. And here, for a jump, the CPU is going to change the program counter and moves to the next state. So on and so forth until the end of the program execution. This is roughly how our computer works. And in this way, the CPU is going to produce a sequence of the states like this. So now for simplicity, let's say user's data is inside the first CPU state, and the result of this program execution is in the last CPU state. This is just for the simplicity of explanation, and we can actually support much larger inputs and outputs than a single CPU state. But let's assume it is in the first and last state like this. Then we can construct a circuit to validate the execution of a RAM program like this. So this circuit contains many copies of a small CPU circuit, and each copy is responsible to check that the 2 consecutive states are correctly computed. Okay? And in this way, the CPU, the whole circuit is going to output 1 if and only if the program execution is correct. Because if there's anything wrong in the middle of the execution, one state will not be consistent with the previous one, and that particular copy will report an error. And then for this particular circuit, the verifier is going to input the program, the input X, and also the result received from the prover. And the prover is responsible to feed in all the other states in this sequence. And the good thing about this construction is the prover does not need to send the whole thing back to the verifier. The prover just proves that there exists such type of sequence that satisfies the circuit. And this is a simplified version of the existing front end for verifiable RAM. One thing I omit here is, to be precise, the CPU also needs to interact with the memory. And it's actually much harder to construct a circuit to validate the memory write and memory read. And in one of the prior work, they construct a very elegant circuit to check the memory consistency. but I'm not going to present the details in this talk. So using this front end, there is actually a trade-off in the existing work between the two categories. So if we zoom in to one copy of this CPU circuit, in one case, if we want the program independent preprocessing, which means the program is not known ahead of time, then this small CPU circuit must be responsible for all possible CPU instructions, because you have no idea which one will be executed during the runtime, because you don't know the program ahead of time. That's why this small CPU circuit is actually consists of all possible instructions side by side, and the size of the circuit is larger. On the other hand, if the program is fixed ahead of time, then we can do some optimizations to identify one or possible CPU instructions at each step. So let's say that if you know your program is going to run addition in the first step, no matter what input you have, then you only need to construct the circuit for addition at the first step. In this way, the circuit is much smaller compared to the first case, but the drawback is that this circuit can only validate one particular program. If you change the program, the behavior will be different, and your circuit is not valid anymore. That's the trade-off in the existing two categories of work. So in our paper, we propose a new construction of the front end. And the key idea of our construction is we are going to generate this circuit on the fly after the execution of the program. So let's say after some preprocessing phase that is independent of the program, the verifier comes up with a particular RAM program and the input, send it to the prover, and with this program and the input, the prover can produce exactly the whole sequence of the state and know exactly which instruction is executed because the program and the data are all fixed. This thing is deterministic. But now the challenge is, how does the prover communicate this information back to the verifier? Right? How does the verifier knows what circuit I'm validating? If you send the whole thing back to the verifier side, it's simply too big. It's as big as the running time of the program. And so if you send this whole thing back, the verifier is actually slower than running the whole thing on her own. So this whole thing is meaningless. So in our paper, we propose a way to solve this problem. So we are going to arrange these states by their instruction type. Okay? So after that, we observe that the same type of instructions will be packed together. Right? For example, the first whole batch will all be additions, followed by all multiplications, and then all memory loads, all jumps, and so on and so forth. So it is much simpler for the prover to send the information back to the verifier. The prover can simply send one number to represent how many times each instruction is executed during the whole program. Right? So in this way, the prover needs only to send one value per instruction back to the client, and the verifier can use this information to construct the circuit on the fly efficiently and succinctly. And the final piece of the circuit is we need to guarantee that this new sequence of states is consistent with the original sequence ordered by the execution time. So finally, we are going to construct the circuit to check that these two sequences are permutations with each other. And that completes the whole front end of our work. With this information, the verifier can run the backend with the prover to prove that this circuit will output 1 on the result p of x the prover sent to me. And this guarantees that the result of the program is correctly computed. Okay? And observe that during the whole process, the verifier never receives anything that is proportional to the length of the program. Everything is constant or the same as the number of instructions, no matter how long your program is executing. So finally, we also have some improvements on the backend. So we need to choose the correct backend that is suitable for our application, namely that we don't want the circuit to be fixed ahead of time. So we replace the backend in the existing work with a different construction that was proposed in last year's Auckland. And the key difference is that it requires a circuit-independent setup phase so that we can generate the circuit on the fly without a separate preprocessing. And we also have some improvements on this backend. We construct a linear time verifiable polynomial delegation part and also make the interactive proof part more efficient for the front end we are building. And you can refer to our paper for more details about these improvements. So finally, I just want to quickly show some experimental results. So we implement our system, and these two figures show the comparison with existing systems with program-independent preprocessing. As you can see on the first figure, we improved the prover time by around 9 times compared to the best system so far called OneTinyRAM in terms of efficiency. In addition, on the second figure, we show that we can reduce the memory usage on the prover side by 120 times, which enables us to support validating a program that is much larger than before running on the same machine. So we can achieve validating a RAM program up to 2 million CPU cycles versus 32K as before. In addition, we also test a bunch of many RAM programs like porting tracing, merge sort, string search, and matrix multiplication. And we show that in terms of prover time, again, we are faster than OneTinyRAM, and even compared to a system that requires program-dependent setup called Buffet, the performance is comparable and sometimes faster than this system. And remember, this system requires a separate setup phase for each program you want to run. And we also have some other optimizations for particular programs to get some additional speed up, and you can refer to the paper for more details. And finally, we do have some drawbacks. We do increase the proof size and the verification time. But as I said, these are usually not bottlenecks of the system. So we can still reach less than 200 kilobytes of the proof size and less than 100 milliseconds of the verification time on all instances we are running for Verifiable RAM program. And finally, this work on its own does not support zero knowledge. But we are working towards making it zero knowledge. And you can take a look at our paper on ePrint. And actually, the paper in the next talk is going to give a zero knowledge version of the backend. To sum up, in this paper, we propose a construction for verifiable RAM that requires program-independent preprocessing. We have optimizations both on the front end and the back end. And also, we implement the whole system and show that it is 1 to 2 orders of magnitude better in terms of prover time and memory usage. So that's all of my talk. Thank you.
Please come up to the microphone if you have questions, and I'll remind you if you can state your name and affiliation before the question. Since this is the cryptography session, it's also okay to state a hash of your identity instead if you prefer to keep anonymous. So come up with questions. Let me start with a question. So I didn't quite understand how when you connect the subcircuits that now the verifier just has a count of them. They know that the prover executed them and connected them with the inputs in the correct way. Is there a way to ensure that?
What do you mean by connect them?
Provided the right inputs and executed the subcircuits in the way that the function required.
Actually, that is related to the backend, because the backend of this, like a different backend, requires only the verifier knows the succinct description of the circuit, namely how many copies do we have, and the connection within each small copy of the CPU circuit. And that's enough for the verifier to talk to the prover and make sure that the result produced by the circuit is correct.
Okay, one more question. So that, and I think you hinted getting towards this at the end of the talk, but one of the things that really makes these kinds of systems very compelling is if there can be private data for the prover that's part of the function you're computing as well. Can this construction, can you imagine extending it to support that?
Yes, that's a very good point. So as I said, we actually already posted the zero knowledge version of the backend, meaning that the circuit itself can be made zero knowledge. But our front end will leak some extra information because the optimization we are doing, the prover needs to send back how many times each instruction is executed during the program. And this sometimes could be sensitive for particular programs. So if you want full zero knowledge, you can still use the old version of the reduction, meaning that like you just give an upper bound of all possible instructions. And that's still good. prover efficiency will be a little bit slower, but this can give you a trade-off in terms of zero knowledge that leaks no information.
Okay, great. So let's thank Yupeng again.